Welcome into this video where we're going to get into a statistics problem where we're looking at finding the probability of some sample mean of a distribution. Now, in this problem, we're going to be talking about one to two different concepts, but primarily central limit theorem, but it's related to another concept that we call sampling distribution. But we're going to read the problem first just to get acquainted with it again. And then we're going to get into those concepts and then how to set up the problem to solve it. So we're given here an insurance company knows that in the entire population of millions of homeowners, we're going to say in the US, the mean annual loss from a fire accident the mean is $500 and the standard deviation is $2,000. Now the distribution of losses, which is the population at hand, we're told is rightly or strongly right-skewed. Most policies have $0 loss, but a few have large losses. If the company sells 10,000 policies, what is the population that it can safely base its rates on the assumption that its average loss will be no greater than $520? So I feel like there's a lot to unpack here, which is why we're going to take our time and take some time in this video to get into the concepts related to this scenario. Let's start with the context of it though, right? The story is we're talking about an insurance company. Now let me get my highlighter going. Okay, we have this insurance company that deals with certain types of accidents or issues in the home, right? And we have this data, summarized data though, of loss due to fire, okay? Now that has to do with what we call our random variable, which you can think of as the focus of the study, right? What is the study's interest? And this goes back to like the first chapter, the first topic in the entire course of statistics, right? This is our variable. Now, they tell us that the distribution of losses, remember that is of the population. They're telling us what that distribution looks like, and they're describing it as right skewed. Now I drew that here right below the problem, okay? And that's what, as you can recall as well, what a right skewed graph looks like for a distribution that is right skewed. And it says strongly right skewed. They even break down how this is the case. Most policies have $0 loss. And what that probably means is the issue that happened at the house wasn't as big of a problem where there was any monetary loss, right? And very few of the fire issues that come through the insurance company are actually large. Well, that creates a right skew distribution where there's fewer data points to the right, and majority of the data points are to the left. And when we read a graph, which is from left to right, we see that the values to the left are going to be smaller than the ones to the right, right? So beyond that point, it then gets into information about a sample. It says if the company sells 10,000 policies, well, that's going to be our sample size, which of course we'll get into in a bit when we talk about central limit theorem. And then the question at hand is, what is the probability that that the company can safely base its rates on the assumption that the average loss will be no greater than $520? Average loss, right? So we're still talking about the mean. So let's get into the concept of central limit theorem. I'm actually going to use mainly this site, but I'm going to point out a couple other sites, okay, which I will link to this video at in the answer, okay, to this question. But we need to understand or just review back to relate back to the definition of central limit theorem. All right, now Scribbr.com does a really great job of this, of explaining a lot of different concepts. Right. So it says that the central limit theorem states that if you take sufficiently large samples from a population, right, over and over and over again, the samples means will be normally distributed. So it will eventually come to a symmetrical distribution, even if the population isn't normally distributed. So if the population is normally distributed, you don't have to worry about sample size really, but sample size is still a big deal. And that's really the central point of central limit theorem. Okay. And other sources get into this. If you have learning material for your class, it also talks about this. The fact that if the sample size is at least 30, okay, it's going to do pretty well in approximating as normal, that distribution of the sample. Okay, so here's a quick example dealing with the central limit theorem. We have a population here which follows Poisson distribution. Notice that the population is skewed, specifically to the right. But if we take 10,000 samples from this population, okay, each with a sample size of 50, so the individual sample, or each individual sample has 50 items, 50 subjects in it. Okay, so it's large enough substantially. The sample means follow approximately a normal distribution, and thus applying to the central limit theorem. Notice the word predicted, theorem, okay? You do want to keep in mind that it is theoretical, okay, for the most part, because what we're dealing with is the sample is being looked at, is being used to study the population. So at the end of the day, from the sample and from the statistics, do we really know if it will produce a normal distribution when we consider multiple samples, right? Theoretically, we'd say it's probable, right? But practically, maybe not. And that's for further empirical research and further observation of the actual population. But it's going to take sampling, which is the whole point of statistics, right? So check out this source if you want to get deeper into it, because it talks more about sample size, okay? And there's something else. Let me see if I can pull it up real quick, because I really liked what this other source talked about or detailed. Okay, let me see if I can find it real quick, because I had it in my mind to bring up, but I'd rather just read from it. And it looks like I've misplaced it, but it's definitely in this article right here. And there's a lot that is unpacked. So instead of taking the time out of this video, which we're focusing on the question, taking the time out of this video to get into the theory of it and re-explaining it, I'd rather just leave this for you to dive into further in your own study time. Okay. So I'll leave it for now, because man, it was a great point. So I would definitely link I'll definitely link those to this video. Now, related to central limit theorem is sampling distribution. There's a sampling distribution for sample means and for proportion. We're focusing on sample means because the problem at hand is dealing with the parameter of the mean, right? And central limit theorem is actually focusing on those two parameters, the mean and the standard deviation. Okay, it takes those two parts. So what that means is we have to make sure we have a mean and a standard deviation for the sampling distribution as it relates to the central limit theorem. So for the sampling distribution of sample means, which involves then that sample of 10,000 policies, we're going to identify or calculate the mean and the standard deviation of that sampling distribution. And this is what it is, okay? So for the mean of the sampling distribution, we tend to just estimate or approximate it as the same as the population mean if it's known. But for the standard deviation of the sampling distribution of the sample mean, X bar, we're going to take the standard deviation of the population and divide it by the square root of n. Another term that we use to refer to this is the standard error. So if you've heard or you recall standard error, that's what we have right there. Okay, so let's go ahead and make note of that, because then this is what we're going to use in calculating. All right, so the mean, as we were told in the problem, excuse me, is 500. So therefore, the mean of the sampling distribution, which you can see there I labeled mu sub x bar. That is also 500. Moving along, we have the standard deviation of the sampling distribution. So we're going to take the standard deviation of the population, which is 2,000, and divide that by the square root of 10,000. Now the square root of 10,000 is 100, right? So 2,000 divided by 100 is going to leave us with 20, okay? You can see there 100 cuts into it pretty evenly, leaving just 20 as a factor that represents the standard deviation or the standard error, okay? So you saw it momentarily up here as I pointed out the rightly skewed distribution. To the right of it is the sampling distribution of the sample mean. And you can see I noted as the normal distribution with a mean of 500 and a standard error, standard deviation of 20, okay? And you can see there it takes on the bell-shaped curve. So when we're dealing with the sample mean or the sampling distribution of the sample means, right, it's going to take on a normal curve. Therefore, we can use the z-score. And that's what it all boils down to and leads to. So to finally answer the question, what is the probability that its average loss will be no greater than $520? We're going to first take the 520 and, excuse my reverse of that. So 520 and convert that into a z-score, right? And basically what we're doing is we're finding the area through the z-score. Okay, make sure I can, there we go. So what I'm going to do is create the shading. So it looks like my colors are not changing, that's fine. So I'm going to replace that with 500, and here's 520 as our X bar value. And we're going to be looking for this area that I'm shading in to the left. And the reason why is it says no greater than, right? Or no more than, which means we're dealing with an inequality such as this as it relates to the X bar symbol in 520. We're going up to 520. That means we have a left area or left area to the left that we're looking for. Okay, so now we're going to plug in the information to that formula, which sometimes is called the central limit theorem formula, all right, or the formula for CLT. And you can see that the formula for the standard error is plugged in, but you could just plug in the value after calculating the standard error separately. So that's going to be 520 minus 500 over 20. And what's really nice is it's just 1, okay? Really easy stuff there. All right, so now we're going to write, again, the probability statement, which is the probability of X bar less than $520, which is the same as saying the probability of less than the z-score being 1, right? If I were to take this curve, in fact, let me just do that and demonstrate it. Okay, we're going to take the curve there that is the normal distribution of the sampling distribution, and now we're going to convert it into the standard normal distribution. And we know that in the standard normal distribution, the mean is always 0, and our z-score there is 1. So same, curve, same area. The only difference is now we're referring to it in terms of z. Okay, now the last thing is this, and what I'm going to have to do momentarily is just pull up my z chart so that way I can demonstrate that. Okay, so we're going to return back momentarily. Okay. All right. So here's our z-score chart, z-table, however you want to call it. And we're going to look for the area using the z-score. And our z-score is 1 or 1.00. Let me use a different color. All right. So if you've ever used a chart, this should look familiar. But what we're doing is we're taking the z-score, breaking it up into two parts. That is 1.0, okay? Pretty much the ones place with the tens place. And then the other part is the hundreds place, out to the hundreds place, okay? So when you add those two together, you get back the z-score. And where they cross is our area, which is 0.8413. So there's our probability, right? The probability is going to be 0.8413, or if you want to write it as a percentage, 84.13%. Okay, so again, I will include the links to some other further studying of central limit theorem, which I think does a great job of breaking it down. And of course, you can go beyond that, but I hope this here was helpful in showing you how to set it up and linking it to the concepts that help to explain or support why we are doing the things that we do here, okay, to answer this question. And let us know if you have any other questions here at Wyzant.